Open your notes to page 41. On page 41, you'll see this is section 1.6 called Transformations of Functions, and today we're going to focus on looking at the graphs of some common functions, and we'll see how different actions affect the graphs of those functions. So the first page of these notes has a chart that actually I took out of your book. It's from page 179. It's a chart of graphs of common functions. Now we've seen some of these before, and this will sort of be our basis for today. And so you need to know, be able to identify these functions based on their equations. You have to know sort of their general shape. And the first thing that we're going to do is fill in some information about each one of these. So let's do the first one together. F of x equals c. It's what's called the constant function. So c is just a constant, just a number. So here it looks like it might be 1.5. And let's take a look and fill in the domain, range, where it's constant, and some more information. So the domain we can see from this graph is all real numbers, right? Negative infinity to infinity. But the range, the set of y values, the only y value I'm allowed to get out is c. And we can write that using our curly brackets. The range is just one value. There's only one possible y value we can get out of this function. And this is called the constant function, so we can see from the graph that it's horizontal, and so it's constant always, or from negative infinity to infinity. And the last bullet point here on all of these that's blank is to decide if a function is even or odd. So remember we talked about this a while back, and from a graph a function is even if it's symmetric about the y-axis, and it's odd if it's symmetric about the origin. So we can see that if we were able to take our paper and fold it along the y-axis, that both sides of this graph would land on top of each other. And so it's symmetric about the y-axis, and so this is an even function. So what I'd like you to do is pause the video and see if you can fill in this information for the rest of these graphs on this page. And this will be good practice for your quiz next week because this is all from sections 1, 2, and 1, 3. So pause the video, try to fill out the rest of this information, and then we'll go over it together. Okay, let's take a peek. So the second function is called the identity function, f of x equals x. It's called the identity function because what you put in, you get out. So the domain and the range are all real numbers. There's no restriction on what I could put in or get out. It's always increasing, and it's an odd function. It's symmetric about the origin. The third function is called the absolute value function. F of x equals the absolute value of x. And so we take our input and we take its absolute value. Well, we can do that to any number we want, so the domain is all real numbers. But when we do that, we won't get anything negative. So the range is from 0 to infinity. It's decreasing from negative infinity to 0, but it's increasing from 0 to infinity. And we can see the symmetry across the y-axis, so it's an even function. In the bottom row, the fourth function is called the standard quadratic function, f of x equals x squared, and we've seen this one before. We can square any number we want, so its domain is all real numbers, but when we do that, we won't get anything negative, so the range is from 0 to infinity. It's decreasing for negative numbers, but it's increasing for positive numbers, and it's an even function. The next function is called the square root function, f of x equals the square root of x. Its domain is only from 0 to infinity, right? Because we talked the other day about not being able to take the square root of a negative number. Its range is also from 0 to infinity. When you take the square root, you won't get a negative number. And it's increasing from 0 to infinity. This is a function that's neither even nor odd. It doesn't have either type of symmetry. And then the last one is called the standard cubic function, f of x equals x cubed. Its domain and range are all real numbers, it's always increasing, and it's an odd function. So make sure you know the names and sort of the equations and just the general shape of these. So anytime you see x squared, you know that that is a quadratic function, and that's what it looks like. Anytime you have the absolute value of x, it has this V shape. And so we'll work with all these functions today. So flip to page 42 and we'll look at example 1. It says graph f of x equals x squared and g of x equals x squared plus 2 in the same coordinate system by making a table first. What do you notice? So our big goal for today is going to be to decide how changing these equations, so how this plus 2, for example, changes the quadratic function, the standard quadratic function. And our goal is also to move away from having to make a table every time we graph and just be able to use the information we know. But we'll start this one out by making a table. So let's make a table and pick a few x values. We can make a table for f of x and g of x together. If you're more comfortable making two tables, that's fine. So you know that the domain of the standard quadratic is all real numbers. We can plug in anything we want, so we can pick a couple of negative values, we could pick 0, and we could pick a couple of positive values. So I chose the integers from -2 to 2. You can certainly pick more points or different ones if you'd like. Pause the video, either finish out this table or finish out the table of values that you'd like to, and then we'll see if we can graph this. So to get my values for f of x, I take my x's and I square them, right? Those all become positive. And then g of x is x squared plus 2, so I can take my values that I just got from f of x and just add 2. So if I plug in -2, I get 6, -1, I get 3, 0, I get 2, 1, I get 3, and 2, I get 6. So here's our table of values. Now pause the video, graph both of these functions in the same coordinate system so we can see a relationship between them, and then we'll talk about what happened. Now that you have both of these functions graphed, let's look at the relationship between the two. So you should have two of these parabola shapes, right? X squared is that standard quadratic that we just talked about on the last page. But x squared plus 2, if you look at your graph, it's the same shape, it's that same graph, it's just moved up 2 units, right? So we can make that observation that g of x is f of x moved up 2 units, right? So all we did really was pick up the blue graph here, pick up x squared, move it up 2 units and plop it down. And so this is what we call a vertical shift. So if c is a positive real number, the graph of f of x plus c, we can fill in these blanks, the graph of f of x plus c is the graph of f of x shifted c units up. And the graph of f of x minus c is the graph of f of x shifted c units down. Now if you think about what this notation is saying, f of x plus c and f of x minus c, this is that we're either adding or subtracting to f of x, and f of x is the same as y, right? So we're adding or subtracting to the y values. And so it should make sense that we're moving vertically, we're moving up and down. Let's take a look at example 2. This says graph f of x equals the absolute value of x minus 3, and I'm going to add to your directions here. Do not make a table. So we're going to use a different method, and we're going to just use what we talked about with vertical shifts. So we can see that we're taking the original absolute value function, and we're taking 3 away from all the y values. And so we know that this is going to look the same as the original absolute value function. It'll just be shifted down 3 units. So what we'll do is we'll start by graphing the original absolute value function and put a couple of points on that graph. And then we'll move point by point and we'll shift this graph down. So set up your coordinate axes. We'll label a couple of values here. And the first thing that we'll do is we will graph the absolute value function that we talked about on the first page. And so we can easily go point by point. We don't have to make a table. We know that if x equals 0, then the absolute value of 0 is just 0, right? So we have a point at the origin. We know that if x is equal to 1, the absolute value of 1 is 1, so I need to label my y-axis here too. So we have the point 1, 1. Right, we have the point 2, 2. The absolute value of 2 is 2, right? 3, 3. But then the same thing on the other side. Negative 1, 1. Right, the absolute value of negative 2 is 2. The absolute value of negative 3 is 3. So if we connect these, we've got that V shape that we saw on the first page. So this is just the original absolute value function. Now what we're going to do to graph what we want to graph, absolute value of x minus 3, is we're just going to pick up each point and we're going to move it down 3 units. So let me get some negative y values here, and I'll do this in a different color. We'll do this in red. So if we think about picking up the point at the origin, 0, 0, and moving it down 3 units, it'll land on 0, negative 3. Right? If I go to the right and I pick my next point, 1, 1, and I move it down 3 units, 1, 2, 3, right? It's going to land on the point 1, negative 2. Same thing with the next point. If I take the point 2, 2 and I move it down 1, 2, 3 units, it lands on 2, negative 1. And if I take the point 3, 3 and I move it down 3 units, it lands at the point 3, 0. And then we can do the same thing on the other side, pick up each point and move it down 3 units. So if this is going too fast, you might want to pause the video and finish putting in these points, and then you can connect them. And so in red, we have the graph of the absolute value of x minus 3. So again, I want you to notice we didn't just make a table and plot points, because now we know something about this function. We know its shape. We know that it's a variation of the absolute value function, so we know it's going to have that V shape. And we also knew that it was that same function, that absolute value function, just moved down 3 units. So we can just move point by point. So it might be helpful to make yourself a note here that we can move point by point. That's what we did here. Make sure that your graphs are well labeled. You can't just start with a V shape at the origin and then move it down and label it negative 3 and expect full credit, right? We see our points here, we see our x and our y values, so make sure that those are well labeled. Okay, before we go on to page 44, I want to show you something that I would have shown you in class today. I want to show you the couple of different graphs and variations of the absolute value of x, and we're going to talk about what happens if instead of adding or subtracting two y values, what if I do that to the x values in the function? So in our red graph here, this is just the graph of the absolute value of x. And the second graph that I want to show you is the absolute value of x minus 4. So if you look at its equation over here, g of x equals the absolute value of x minus 4, you might think that moving over, or that subtracting 4 from the x values means that the graph goes left. And then we see the third one is the absolute value of x plus 6. And again, we might think that adding 6 to our x values means we go right. And let's see what happens. So now I've added in the graph of the absolute value of x plus 4, and that's the blue graph, and it's to the right of the original graph. So it's a little bit counterintuitive to what we might have thought, but let's think about our x-intercept. So in the red graph, absolute value of x, the x-intercept is at the origin. If we had the absolute value of x minus 4, and we wanted to find the x-intercept, we would set the function, we would set y equal to 0, and we'd solve for x. And just think about what would have to happen for us to get 0 out of this. Our x value would have to be 4, right? So that we have the absolute value of 4 minus 4, which is the absolute value of 0, which is 0. So that tells us that our x-intercept has to be 4, which sort of justifies why we're moving over to the right 4 units instead of to the left. So it does match our graph. And then if we take a look at the absolute value of x plus 6, so now I've got 3 graphs and that new one is in green, you can see that that moves to the left. And so what this tells us is that if we add a constant to the x value, it shifts our graph left, and if we subtract, it shifts our graph right. So let's fill that out. Now flip to page 44, and we will fill out those 2 facts. And this is what's called a horizontal shift. Again, let c be a positive real number. The graph of f of x plus c is the graph of f of x shifted c units left. And the graph of f of x minus c is the graph of f of x shifted c units right. So let's try an example, example 3. I'll have you pause the video and try this on your own. But again, I don't want you to make a table. So don't make a table. So you're going to graph f of x equals, in parentheses, x minus 2 all squared, and you can follow the method that we just used in example 2. You can graph the original function, x squared, and then you can move it over right 2 units. So it might be helpful to make a note of that f of x is the graph of x squared moved right 2 units. So pause the video and see if you can use the method from the last example to get a good graph here. Okay, let's take a look at the graph together. So a good method is to start with the graph of x squared, the standard quadratic. You know what that looks like. And then we're shifting it over to the right 2 units. And so in orange here, we have the graph of x minus 2 all squared. Now, again, make sure that you don't just have 2 parabola shapes, 2 quadratic functions there. I should be able to clearly see your points and where they are. So the x-intercept of the graph of x minus 2 squared is over at x equals 2. The y-intercept is at the point 0, 4. I should be able to clearly see these things labeled on your graph, whether they're labeled as points or whether they're labeled using your axes like I have here. Let's flip to page 45, and on page 45 we'll talk about the last 2 types of transformations. So we've already talked about what happens if I add or subtract to the x values or to the y values. We can shift a graph up and down, left and right. The next thing we're going to talk about is what happens if I change the sign of all the y values or all the x values. So on the top of page 45, this is what's called reflections. So the graph of negative f of x is the graph of f of x reflected about the x-axis. And if you think about y, all we're doing is changing the sign on all the y values. So if my y values, say, were positive, and then I change the signs, they're going to become negative. So if they were above the the x-axis, then they go below, right? If they were negative, they become positive. So if they were below, they're going to go above. And we'll take a look at an example in a second. But the second bullet point here says the graph of f of negative x. So I'm making x values negative. So if I'm making x values negative, I'm changing their sign. Then that's the graph of f of x reflected about the y-axis. And for the same reason, because if I change the sign on my x values, the x values that were positive, right, or to the right of the y-axis, are going to become negative, so they'll go to the left. So we're seeing that reflection across the y-axis. Before we fill in any more on this page, I want to show you a couple of graphs like I would have done in class today. So let's just look at this reflecting idea so we can visualize it. Off to the side here, it tells you what the name of each of these functions is and the color that it's using. So in red, we have the graph of the square root of x. This is the standard square root function that we talked about at the beginning. And if we put a negative sign in front of it, so if I want to graph, say, g of x equals negative square root of x, we just said that we're making all of the y values, we're changing the sign on all the y values. So if you look at our red graph, all the y values are positive, right? If we change the sign on them, they're all going to become negative. So we end up with the same looking graph, but below, right, the x-axis. It's a reflection across the x-axis. And so this is our new graph here, negative square root of x in blue. So we've reflected across the x-axis. Now, what if I did the opposite? What if I did f of negative x? And we just talked about this is going to be a reflection across the y-axis. So f of negative x is the square root of negative x. And so the first thing you might think of is I can't do that. I can't have a negative in the square root. But think about what the domain of this function is. In order for this to be allowed, x has to be negative, right? So the domain of this function, this third one we're going to graph in just a second, is negative infinity to 0. So let's take a look at what that looks like. So this graph is going to be in green. And here we have the square root of negative x. So this is a reflection across the y-axis. Right? So all three of these graphs have the same shape, but it's sort of where they're positioned, right? So we took the red graph originally, we reflected it across the x-axis when we had negative square root of x. And then we started over and we reflected across the y-axis when we have the square root of negative x. Now before we go back to page 45 and talk about the last type of transformation on a function, let's just look at some graphs and see if we can figure out what's happening. We're going to take a look at our familiar standard quadratic function x squared again, that's graphed here in red, and then we're going to do a couple of new transformations on it. So the first thing that we're going to do is we are going to multiply it by a constant. We're going to multiply it by 7 and see what happens. So if I think about multiplying by my function by 7, really what I'm saying is I'm taking my y values and I'm multiplying them all by 7. So while my x values are staying the same, my y values are getting bigger, right? Let's see what happens to the graph. Here we have that graph of 7x squared in blue. So our original function is in red. And look, we've got that same shape, that we call this a parabola shape, the same shape, but it's taller and skinnier. It sort of tightened it up, right? Because again, we made our y values bigger by a factor of 7. And then let's see what happens when we multiply our function by a smaller number, say 0.04 times x squared. And so I'm taking all of my sort of original outputs from x squared, my original y values, I'm multiplying them by 0.04. That's going to make them small, right? So we should expect that this graph looks sort of a little bit lower than the last graph, and let's take a look. So here in green, we have 0.04 times x squared. We still have this same shape, but look at how wide it is. It's really squished down because again, we took all of our y values and we made them smaller by a factor of 0.04. So this is our last type of transformation. It's called stretching and shrinking graphs vertically. We can also do this horizontally, but we're gonna skip that for now. We might come back to it later. Now let's flip back to page 45 and we'll finish out these notes. So on page 45, we already talked about reflections, and let's talk about stretching and shrinking graphs vertically, what we just saw in the last slide. So let C be a positive real number. If C is greater than 1, and we multiply our function by that value, so we used C equals 7, we saw that this graph got sort of tighter, taller, and skinnier. We call this a stretch. So if c is greater than 1, c times f of x stretches the graph vertically. And then we tried a value that was less than 1, but we also didn't make it negative because that would take us back up to reflections. So if c is a number between 0 and 1, that was our 0.04 that we used, c times f of x, we say, shrinks the graph vertically. And we can think about shrinking as sort of squishing the graph down versus stretching it, sort of tightening it up. And so that really takes care of all of the types of transformations that we can do on functions that we'll talk about. So just a quick recap before we look at some examples where we put it all together. We can shift a graph, so we can pick up and move a graph vertically or horizontally, up, down, left, or right. We can also take a graph and we can reflect it across either axis, and we can take a graph and we can stretch it or shrink it vertically. Again, we'll skip horizontal shrinking for right now. We might come back to it. When we have graphs that have multiple transformations on a function, the order does matter. And so we sort of have to respect the order the way that we do order of operations. And so we do our horizontal shift first if we have one, then we either stretch or shrink depending on what we have, reflection, and vertical shift last. So the next 4 examples are examples where we're going to put these transformations together and make sense of them. Let's take a look at example 4 first, and then I'll let you try example 5. So example 4 says, describe how g of x equals negative 3 times x plus 4l squared minus 1 is a transformation of x squared. And so we have to see what all the pieces mean. So the first thing I'll write is that we start with x squared. And then let's think about what we do to that function and think about how this order matters. So we'll start with horizontal shift. And we see that we do have a horizontal shift because of that x plus 4 on the inside. And so the first thing that we'll have to do is shift left 4 units, right? Then the next thing that we will do, let me just make my font size a little smaller so I don't run out of room. The next thing is, do we have any stretching or shrinking? Well, we do, because we've multiplied this function by 3. Well, it's really a negative 3, but we'll treat those as 2 different things because that negative tells us that we will do a reflection too. So let's just focus on the 3. That tells us that we stretch by a factor of 3. And then what about that negative sign? That negative sign tells us that we reflect across the x-axis, right? That negative sign is in front of the function. It didn't happen in front of the x, so it's a reflection across the x-axis, not the y-axis. And then lastly, what about that negative 1? What about that minus 1 at the end? That tells us that we shift down 1 unit. So just to recap and look at our equation here, we started with x squared. That's sort of hidden inside here. All right, we added 4 to our x value. That would be the first thing we did if we were to evaluate the function. So we had to shift the graph 4 units left. And then we multiplied by 3, which stretches by a factor of 3. And then we multiplied by a negative 1, right? We're treating that as 2 different pieces, which tells us we reflect across the x-axis. And finally, we subtract 1, and so we shift down 1 unit. So this is an example of a function that has all of the possible transformations that we talked about in it. That won't always be the case, but this is a nice one to look at. Now pause the video and try example 5. Notice that I didn't give you a defined function. We're just using f and f of x to denote this function. So pause the video and see if you can do the same thing. Just describe how negative f of x minus 2 plus 1 is a transformation of y equals f of x. Let's take a look at example 5 together. So describing how this is a transformation on an original function. So we start with f of x, and what do we do to that x? We subtract 2, right? So we shift right 2 units. Then we multiply by negative 1, so we reflect across the x-axis. There's no stretching or shrinking in this example. And then finally we add 1 to all of the y values that we have, and so we shift it up 1 unit. So even though I didn't give you a defined function that you could have graphed in this example, you can still describe how it's a transformation. Now let's flip to the last page, page 46. We've got 2 more examples to look at, and what I'd like you to do is pause the video and see if you can do examples 6 and 7. I'll tell you that example 7 is a little easier than 6. In 6, I'm giving you a transformation and you have to go backwards and write an equation. So if you're more comfortable starting with 7, then that's okay. So pause the video, try to fill out these 2 examples, and then we'll go over them together. Alright, so in example 6, let's say suppose we took the graph of the square root of x and shifted it 5 units right and stretched it by a factor of 2. Write the equation of this new graph. I'm going to call it g of x, so we don't use f again. So let's think about what we did. We took our square root function and we shifted it 5 units to the right. So that means that we changed x values. So that means that we have to do something inside this square root to our x values. We remember that if we want to shift right, we ask, okay, do I add 5 or do I subtract 5? Right? We saw in our other examples that in order to shift to the right, we have to subtract. So g of x right now equals the square root of x minus 5. That shifts us 5 units to the right. Now, if we want to stretch by a factor of 2, that means we have to take all of our current y values and multiply them by 2, right? So I'm scaling my graph or my values by a factor of 2, and we do that by multiplying those values by 2. So g of x equals 2 times the square root of x minus 5. And finally, let's go over example 7, our last example in this set of notes. The graph of f of x is below graph f of x minus 2 plus 4. And so the first thing you should do is decide what's happening. And so what's happening is that we're taking the original graph f of x, removing it right 2 units, and up 4 units. So what we can do is move point by point, just like we did in some of the other examples. So if we started thinking about maybe these 4 points, even some in between if we needed to, take every point, move it right 2 units and up 1, 2, 3, 4 units and get your new point. Right, so our graph has the same shape. All we did was a horizontal and a vertical shift, right? So we picked our graph up, we moved it to the right 2 units, up 4 units, and we sat it back down. So this is what your graph should look like. Now I know this was a long section and a long video. This is a lot of information. You'll be practicing some examples like this on MyMathLab, so do as much as you can, and then we'll talk more about this on the next class.